I will share my screen. And let's see how much of this we can stomach before we don't like it anymore. Oh, that's my worked out notes. So let's not use that one. Unless you don't want to actually see me do any problems, which I doubt. I once had a professor that did that where they just had their their slides. They had a PowerPoint and they would just hit the space bar or whatever and click and just have the steps pop up and just click through it and not really explain much. One of the worst teachers I had. All right. So last time we took our test, but before that, well, sorry, we didn't take our test exactly last time, but the material we learned between the test and today was parametrics and then polar coordinates. And we both learned how to change from polar to Cartesian for coordinates, but also equations. And we also started some kind of calculus with polar functions. We took derivatives and looked at the first and second derivative tests. Well, this is Calc 2, so we also want to learn how to integrate polar functions. And so we've got these two forms here. And the one that we will most likely use is going to be the first one here, because our functions are going to be given to us in terms of theta. So we're going to want to integrate in terms of theta. I haven't gone back in quite a while. I don't know the origin of this 1/2 off the top of my head. But if you would like, I can go back and do that. But there is a 1/2 in front of any integral that you do in terms of a polar region. So just remember that that's out there. So first, let's go ahead and sketch one of these curves because they're definitely interesting before we even attempt to discuss what the integral looks like. So notice it says sketch the curve, then compute the area. So it says that the curve here, r equals cosine 3 theta. So again, I'm going to do this on the calculator, and then I'm going to go to Mathematica and do it because it's going to do it really nicely for us. So in our calculators, go to mode again. So we're really using all the modes that we can this semester. We've got our function. This time we want to be in polar if you're not already. We want to go to y equals. And we have cosine 3 theta. So we got things like lines and circles and stuff like that the other day. We didn't get anything like this. Okay. So notice the thing says 1 leaf. I'll often say 1 petal, right? Because these things sometimes look like flowers. And notice the one on the calculator here, this one here looks like it's different size than the other two. Well, let me go ahead and do that on Mathematica because it isn't actually, right? Remember, the calculator likes to stretch out that axis because of the viewing window. Okay, so I want to do polar plot. It tells it that I'm plotting in polar coordinates. And I just want to say cosine of 3 theta. And I want theta to run from, let's say, 0 to 2 pi, right? 1 cycle. So you should be able to see that that's symmetrical, right? All three of these are the same size. So that means if it wants us to do one petal, well then, or one leaf, then I can do any of them, right? They're all the same size. So I'm going to choose to do this one that's over here along the x-axis. And now the question is, okay, how do I get this entire leaf? Well, remember that this function is r equals some function of theta, right? So any value that you get along here represents r. So if I'm back here at the origin, or the pole, right, for polar coordinates, my radius there is 0. So what angles can I plug into this thing to get 0? So cosine of what angle is 0?
Pi over 2. Or 90.
Okay. Pi over 2. Anything else?
And then 270 with 3 pi over 2.
Right. And then you could just keep going, right? And then what about if my radius is 1? So what angle here would make this thing 1?
Zero.
So 0 or 2 pi, right?
Yeah.
Okay, so actually, and it's strange, but this thing, right, at 0 degrees starts here and then moves this way. Remember, we had direction when we're doing these. And it goes this way. Now, because there's a 3 in here, this angle is not pi over 2. It's going to be pi over 6, right? Because we want the interior of the cosine, right, the argument, to be pi over 2. So if I were to change this angle here to pi over 6, it should just plot the top half of one petal. And it does that. So now I'm going to integrate over those bounds from 0 to pi over 6. That'll give me half a petal. If I want a whole, then I'll multiply it by 2. Is this making sense so far?
Could you explain again how you get the pi over 6?
So the remember that we said we want the radius, right? This whole function, cosine of 3 theta, to equal 0, right?
Right.
So for cosine of 3 theta to equal 0, 3 theta has to equal the inverse cosine of 0, which means 3 theta equals pi over 2, which is one of those options, right?
Right.
Means theta equals pi over 6.
Okay. All right. Thank you.
Mm-hmm. All right. So we've got 1/2, right? Because that's just naturally there. We know our bounds are 0 to pi over 6. We've discovered that already. And honestly, the absolute hardest part of these problems is graphing them and determining the bounds of the integral. Once you've done that, it's all things you've done already. It's old news at that point. So 1/2, 0 to pi over 6. Our function is cosine 3 theta. but notice it's function squared. So we need cosine 3 theta quantity squared with respect to theta. Now again, that's half a petal, and we are asked for 1 whole petal. So I'm going to do 2 times. All right, so half petal or leaf, whatever you want to call it. Call it leaves, that's what it is on paper. All right, so easily these are gone. Now, what do we do with cosine squared? Anybody recall? Anybody remember this equation? Anybody put a thumb up? I can't see everybody.
So, in this case, would you, since it's 1 plus cosine 2 theta over 2, when you replace it for the cosine 3 theta, would it be 1 plus cosine 6 theta
Mm-hmm. Absolutely.
over 2?
So we've now got integral 0 to pi over 6. I am replacing cosine of 3 theta squared with 1/2 plus, actually let's do 1/2 1 plus cosine 6 theta d theta. So the first one is just going to be d theta. Second one is cosine 6 theta d theta. Do you recall how to do that one? I hope so, because that was the first thing we did in the class. And it was a review even then. So what type of integration technique do I need there?
When Okay. Wouldn't it be sine? Actually, no, because it's a theta. Would it just be sine 6 theta plus? Well, not plus it because it's non-infinite.
It's not just sine 6 theta.
Oh,
We
and you would
need,
divide 6 over it. Or divide by 6.
we need to do integration
Mm-hmm.
or u substitution there, right?
Yes.
So if we let u equal 6 theta, we'd need a 6 inside. And we would need a 1/6 outside, which is how we get 1/6 sine 6 theta. And all of this from 0 to pi over 6.
And what's that 6 doing in front of the cosine?
I just did the U substitution method.
Okay, then. Okay,
Right, I put the 6 in and the 1/6 out.
I got you. And 1 equals, it's because you made the 1 equal to a d theta, so it's just theta. Or the answer would
Yeah,
be theta.
it's 1 times d theta, which is just d theta.
Okay, I got you.
Okay, plugging in. This looks like the back half all goes to 0. In here, these 6's would cancel. So sine of pi, well, guess what? Also 0. So it looks like end of the day, we got pi over 12. Guys agree with me? Okay. So I'm just looking at these other ones here real quick on my worked out sheet to see which one I think would be appropriate to try to give to you guys. Maybe even 2 of them potentially. But that's up to you guys, I guess. This one doesn't look too terrible. It's a quick calculation. All right, I think maybe I'll do 2 more of these, one of the arc lengths, and then let you try one of each. So I'm going to leave that one. And I'm actually going to change this one. Instead of 2 sine theta, which makes, actually you could do both maybe, because that one will be really easy. And then also do sine 2 theta, which is actually an interesting problem. The first one's just a circle, so it's super easy. So I'm just going to say, instead of having to worry about that term, which I believe is pronounced lemniscate, this is just an infinity symbol. So let me go back to Mathematica and plot these. And you guys should be trying to do this on your calculator. In case I do ask you to do this at some point. So we've got 2 functions. One of them is r squared, and I need to plot r. So I need to take the square root of 8 cosine 2 theta. And I also need to plot the negative square root, because you can get positive and negative. And then finally, the other function is just 2. So we should know in polar r equal 2 is just the circle centered at the origin with a radius of 2. And then I'm going to, in this case, ask the program to plot the first two functions as the same color so that it looks like one function. And then the other a different color. And what did we not like? Forgot to give it the bounds. Okay, so theta is going to run from 0 to 2 pi. There we go. Can everyone see that okay?
Yeah.
Thank you. So we've got r equal 2, that's the green circle. And then we've got r equals the square root of 8 cosine 2 theta, which is the infinite symbol, right? Now, if you're having some trouble on your calculator doing this one, I don't know why, but it does not like the infinity one. And because of that, we have to, so here I just did it to demonstrate. And of course now it's actually plotting, maybe I got my, let me look and see here. So let's see, typically I think theta max is 2 pi. Okay, so I made theta max 2 pi. And this is all that I got. Notice how it didn't plot the entire function? And I'm not sure why it doesn't like to do that. So there's two ways to fix it. You can go to your window and there's theta max, second one down. I typically make that larger and I make the step size smaller. Step size being smaller, meaning that it gives more points, and same thing for theta max if you make it bigger. So I think I made it like, I don't know, maybe 8 pi or something.
So when I put in the square root of 8 cosine 2 theta, my graph kind of looks like an X.
So that's what I was saying. You need to adjust these values that I was telling you.
Okay, because I did try to adjust it. There, it's like went to like one little line, it just went as like a X line. So they would, because right now it's set to 360. So should I bump it up more?
So you're in degree mode. Yeah, 300.
Yes.
That's not even.
Yes, I am in degree mode.
Well,
Let me
then
check.
300's not even all the way around,
360.
right?
Yeah. Well, I just put in radiance mode, so I'll see that. Oh no, that doesn't help. Jeez.
So look, I had to, for my calculator, I had to put 9 pi, which came out to 28 something, for theta
Okay.
max,
All right, because
just to get the full curve.
okay, because I put mine in radiant mode and it did not like that one bit.
That shouldn't be a problem.
Okay. Huh.
Now, of course, if you're in the,
Okay.
if you zoom standard,
Oh, worst one to do some standard. Okay.
now, of course, it changed my theta max on me.
Oh, I think what happened was, oh, I know what happened. Okay, that was my mistake. I know what I did now. I set like the boundaries too small for it, so like it was just getting it where it was
But you should
where it
see
made X.
the whole
Mhm.
thing.
Yep, I see it now, and I got on my calculator too.
So if anybody's having trouble with that and they want to ask me about it, then either can we do that while we're doing our breakout sessions, or set up a meeting with me outside of class to do that. All right, so we've got this circle, we've got this infinite symbol. It says in the problem, inside the infinity symbol and outside the circle. Can you all see my cursor?
Yes.
Yeah.
Okay. So if it's inside the infinity symbol and outside the circle, we're referring to this area here that I'm encompassing. But there are two of those, right? There's this here and there's one over here. But we really just need to integrate one of them and then multiply by 2. Now, in this case, these curves cross at 2 points. Well, technically 4, but we've got these 2 points here. Now, the tricky thing is, and it doesn't apply to this problem, but because these, or because of the nature of polar coordinates, a particular point, remember, does not have to be the same angle. So we're going to solve for these and hopefully they'll be the same angle. So let's stop sharing this guy. Let's go back to this guy. All right. So we want to know, when are these two functions equal, right? Because they have to cross. And then we want to prove that those are the 2 points that we see on the graph. One of these is already r squared, and I don't like dealing with square roots. I'd have to take this, I'd have to square both sides anyway. So I'm just going to start with that. And I'm just going to square the other one and set them equal. If I divide by 8 on both sides, then I have this. Take the inverse cosine of both sides and have that. And then finally, if I want theta, that's 1/2 the inverse cosine of 1/2. So in radians, what angles are those? So for the inverse cosine of 1/2, we would get things like pi over 3. I think it's 5 pi over 3. Seven pi over 3. But then we're multiplying by 1/2. So these angles are pi over 6, 5 pi over 6, and so on. So let's see if these angles match up to the ones where they cross on the graph. So how do I do that? Well, I can change my window. So I'm going to go start at pi over 6. Okay. And then the next time we said they crossed was 5 pi over 6. All right, so it looks like this point and this point agree with those two angles, but those aren't the 2 points that I want. What about maybe negative pi over 6? Okay. Not sure why I'm I think maybe because the negative. See if I get rid of this one. There we go. I don't know why when I've plotted that every other time, it never had that other piece over there. That's interesting. Maybe I didn't need the negative one. Hold on a second. Let me check myself here. So this point down here corresponds to negative pi over 6. And this one up here is pi over 6. Now, if you guys have the textbook, or if you choose to look up some of these things later online or something, then one thing they discuss is these points of intersection and how they lay on the same line. So we'll talk about that a little bit in the next problem. But it appears that if we integrate from negative pi over 6 to pi over 6, we pick up the area that we want. And then we just need to multiply it by 2, and we're done. So I know this is somewhat abstract. Is there anybody that's completely lost right now?
So my question is, what is the function of the circle? Is that just 2? Because I know like the little infinite sign is like square root 8 cosine 2 theta, but what is the circle?
It's just r equals 2.
Oh.
Remember in polar coordinates that circles are very, very easily represented, and it's just a number, right?
Okay, I gotcha.
All right, so we've done the hard part of the problem. We've discovered what the 2 points are, and we've discovered what we need to integrate over then. So we found pi over 6 and negative pi over 6 instead of 5 pi. So we need 1/2 integral negative pi over 6 to pi over 6. Then we need the function of theta squared. Now we've got 2 functions, which means I need the first one squared, or the outer one, which is going to be the infinite symbol or the lemniscate. So that's, and it's already squared. So that's 8 cosine 2 theta minus the inner function squared with respect to theta. And then again, the problem, right, this is for one side. It asks for the total area. So we need to multiply by 2 in front.
Dr. Beckins, we can't see that screen. We
Oh,
still
sorry.
both of them.
Come on, you can't see everything all the time? What about now?
Yep, we can see it now. Thank you.
Mm-hmm. Right, so again, it's 1/2 integral from the 2 bounds. The first function squared, it's already squared, right? It's already r squared. And then the second function squared. And I'm subtracting the inner one, just like we would normally do. And then, of course, I put this 2 out in front because we need 2 of the area that we drew out in our graph. So now it's just a matter of what's the integral here. Not so bad, right? The integral of cosine of 2 theta is 1/2 sine 2 theta. Integral of 4. So it's going to be 4 theta. From negative pi over 6 to pi over 6. So this is 4, which means they both have a 4 in common. I'm just going to pull that out. So then we have sine 2 pi over 6. And plug in for the second part. And that was an even function to begin with, so we could have went from 0 to pi over 6 and multiplied by 2. That was another option that we could have done. So we just need to know what's, I'm sorry, go ahead.
Sorry, why did you leave the 4 in?
What for?
Yeah, you're right. Sorry.
Crazy, dude. All right, so we just need sine of pi over 3. Appears that is root 3 over 2. Remember that sine is an odd function. So sine of negative 2 pi over 6 is the same as negative of the sine of 2 pi over 6. So those negatives would cancel. So 2 times root 3 over 2, that's just root 3. And this would be negative 2 pi over 6 or pi over 3. Right? And nothing you can do with that. So that's as pretty as it's going to get. But again, the calculations are not hard here. It's the setup that's difficult. So questions about this guy before we tackle the really tough one? All right, so I'm just going to suppose that you guys can all do this 100% on your own then. I'm going to go ahead and take a look at this guy. I'm going to do one of the arc lengths and then I'll set you loose to try some problems. So once again, very first thing we need to do is plot these two functions. So let me take care of that. So it's 1 plus cosine 2 theta, the other function, 3 cosine theta. All right, so I've plotted these for you. The 3 cosine theta, that's another circle. It's just been shifted. And 1 plus cosine theta, some people think resembles a heart, which is kind of where it gets its name from, right? It's a cardioid. Now the problem here says the area inside the cardioid and outside the circle. So we're talking this region and this region. Now, of course, I'm only going to calculate one of them and multiply by 2. It's much easier. And I want to know this point of intersection and this point of intersection. Now, this one does fall, as I said, along one of those lines. I don't know if I can draw a line on here. See if my pen works. No, darn. I guess I could try this. So if I were to draw a line from the pole out to this point of intersection out here, those two functions cross that line at the same point. So the angle at this point for both of them will be the same. And it'll be the same as, should be this, a representative angle of that. However, at the pole, right, I can't draw a line through there. And so that is not going to be the same angle for both functions, which means when I go to integrate, I need to separate the two integrals. So I'm going to integrate one function over 2 bounds and integrate the other function over a different set of bounds.
And could you go over why the lines aren't the same again? I'm sorry.
So the idea is if you could draw a line from the pole out to the point of intersection, that angle is the same.
Mm-hmm.
But if they intersect at the pole, right, I can't draw a line through that.
Okay.
Right, I could effectively draw any line I wanted, right? It could be any one of these things. So the angle there does not have to be the same. So first thing we need, and again, we're trying to find this area here and this area here. And then we're going to add them together. Or I'm just going to find this one and multiply by 2. So very first thing I need to do is find out where do they intersect. So to do that, I need to set them equal. So I'm going to get 1 equals. I would subtract the cosine to the other side. Right? So question is, what are those angles? And to save some time, I'll give them to you. So they appear to be pi over 3 and 5 pi over 3. So let's go back and look at the plot. So let's go 0 to pi over 3 and see what it looks like. Okay, so clearly that's not the piece that we wanted. But it does appear that pi over 3 is where they intersect over there, right? So that is the angle pi over 3, so that's good. So notice both of them start at a different value when the angle is 0, but when the angle is pi over 3, they both intersect right there. So in fact, we need to start at pi over 3, and we need to run to a different angle. Now, again, that angle is not going to be the same for both of them. So remember that we were talking about the origin here, or the pole. So when does f of theta equal 0? So that's when the cosine of theta equals -1, or when theta is the inverse cosine of -1. So the question is, what angles are those? Anybody know?
Pi?
Why did you say it like it was a question?
Because I don't have the unit circle in front of me.
Okay, so pi. So let's go back to our graph. But this time, let's integrate, or sorry, let's just graph it from pi over 3 to pi and see what happens. Okay, so that does pick up the part of the cardioid, right, the red function that we want. However, look at the circle. From pi over 3 to pi, the circle's almost all the way back around, right? So if we tried to integrate both functions from pi to pi over 3 or pi over 3 to pi, does it make sense to you that you'd be picking up way too much area? Or you'd be integrating the circle for far too much?
Yeah, that makes sense.
Okay. Then the other one we need to do is, when does 3 cosine of theta give back 0? Well, that's 0. I'm sorry, not 0, pi over 2. 3 pi over 2 and so on, right? So again, let's go back. I hope I'm keeping track of what I'm sharing properly here with you. I'm sure you'd be the first to tell me. So we just said pi over 2. So now if we look at the graph, let's maybe shrink it a little bit here. Now we can see the circle starting at pi over 3 gets us back to the pole for pi over 2. So in order to properly pick up the areas that we want, we need to integrate the cardioid squared, right, because it's f of theta squared. The cardioid's going to start at pi over 3. And over here, we had shown that at pi will get us back to the pole. Now the area of the circle is inside of that guy. So if we want to take the area outside, right, we need to subtract. And then we've got starting at pi over 3 again, but the circle only needs to go to pi over 2. And again, that only gives us 1/2 the thing that we want, so multiply everything by 2. So again, setup, tough. From here on out, not so bad. So I'm just going to go ahead and run through this calculation. And if you have any questions, feel free to ask them as I'm working. All right, so putting this one back together now. I've got d theta, then I've got another d theta, or another half d theta down there. So that's 3 halves. Whoa, where are we going? All right, so now we can integrate everything. So this is going to be 3 halves theta plus 2 sine theta. One fourth sine 2 theta. Oops, looks like I started accidentally writing pi over 2 for this one. It's pi. There we go. All right, 9 halves. It's going to be theta. 1/2 sine 2 theta. Pi over 3 pi over 2. Computer. And to save us all some time, headaches. Trying to find a solution to this one. All of that nonsense. Looks like it comes out to pi over 4. Make sure I multiplied that by 2. Beginning. Yeah, okay. So all that comes out to pi over 4. So questions about that problem?
I just don't think I could ever do that by myself.
I wouldn't say that you'll never be able to do it by yourself, but maybe not, tomorrow.
Yeah,
I think this problem is probably the toughest problem in all of Calc 2 that I gave to you guys. And simply because we're not used to polar coordinates. The we're doing integrals, which we're familiar with, but we're not familiar with necessarily ever having to do it over different intervals. So it's kind of the word that keeps coming to mind is abstract kind of calculation. We're just not used to it. All right, so I've got, I would like to do one arc length problem, which we've done multiple times now. I think this is our third or fourth time doing arc length. All right, because we did it for Cartesian, we did it for parametrics. And I guess this is our first time doing it for polar, so it'll be 3 times. So again, formulas given here to you. The length of an arc for a polar function. We just need r squared, and we need drd theta also squared. The sum of those squares square rooted. So it's as simple as taking the derivative, substituting the original function of the derivative in, and then following through with the integral. So this first one here is just 2 cosine theta. drd theta is minus 2 sine theta. So arc length is the integral. They gave us the bounds, so we don't have to figure those out, which is nice. Plug in all the appropriate parts and square them. So this is going to be, looks like 4 cosine squared plus 4 sine squared. That's amazing. So I can factor out that 4. And then I've got sine squared plus cosine squared, which we all love because it's just 1. Square root of 4 comes out as a 2. And we just have to integrate good old d theta. So this is 2 theta from 0 to 5 pi over 6, or 2 times 5 pi over 6, which is 5 pi over 3. So not that one, definitely not hard. Process itself, not terrible, right? Got the formula. Just need to be able to take a derivative and then remember all your integration techniques. So I want you guys to do part B there. And I think it was part B for the polar areas. And that'll be all that I have for you today, unless you guys want to ask questions or start reviewing.